Welcome back to the Art of Climate Modeling. In today's lecture, we'll be talking about some of the choices that get swept under the rug in atmospheric dynamical cores, including numerical diffusion, filters, and fixers. These methods have been designed to augment the numerical methods we've discussed in the past lectures in order to maintain some desirable physical properties that may have gotten lost because of the discretization process. To begin, let's get to the heart of the issue with discrete methods. As we discussed in the context of spectral transform methods, nonlinearities in the equations of motion are responsible for effects that cause mixing across wave numbers. In the case of the atmospheric fluid equations, these nonlinearities are responsible for driving a cascade of energy from larger scales to smaller scales. Even our discrete representation of these equations exhibit this energy cascade. You can think of this energy cascade in the context of a steepening ocean wave. Initially, the wave may have a long wavelength associated with it, but as it heads towards shore, the wave steepens, and the spatial scale associated with that wave front shortens. This is, in effect, a consequence of energy moving from longer wavelengths into shorter wavelengths. In the atmosphere, the amount of energy present within each wave number is approximately governed by Kolmogorov's theory of turbulence. For 2D flows, like those in a stratified atmosphere, we anticipate energy to decay in accordance with a power law with coefficient -3. For 3D flows, where turbulent eddies are much shorter than the scale height of the atmosphere, energy decays in accordance with a power law with coefficient -5/3. Energy is continuously streaming from large scales into smaller scales, and being provided at the largest scales by large-scale forcing such as global radiative forcing. So what happens when we artificially cut off which wave modes can be represented? Keep in mind, the shortest waves that can be represented by the discrete system are 2 delta x modes, that is, alternating patterns of 1s and -1s. So for models that have grid points that are 100 kilometers apart, the shortest wave that can be represented is 200 kilometers long. What happens if our discretization tries to transfer energy into wave modes that are shorter than 200 kilometers? By using a discrete grid spacing, we impose a truncation scale on the system, that is, a maximum resolvable wavelength. As a consequence, the transfer of energy into shorter modes leads to an effect known as aliasing. That is, when the system tries to add energy at a scale that cannot be represented by the discretization, it is instead reflected back into the domain of resolved wavelengths. The result is an accumulation of energy at the bottom of the energy cascade and an enhancement in the shortest wavelengths. This is a highly unphysical phenomenon, and one that manifests in the form of spectral ringing. Aliasing is a natural consequence of energy conservation. If energy cannot manifest at the smallest scales, then it must show up elsewhere in the energy spectrum. In the real atmosphere, there is a smallest scale for turbulent features known as the Kolmogorov microscale. At these scales, the timescale of the physical viscosity is greater than the timescale of advective transport, and so energy is converted from kinetic energy into thermal energy. However, in the real atmosphere, this process occurs on scales of millimeters, which is far below the scale of any sort of resolved flow in our atmospheric dynamical cores. Thus, our typical truncation scales in atmospheric models are nowhere near the truncation scale of the real atmosphere. The problem of energy accumulation at the finest scales is universal and independent of the choice of spatial discretization, time-stepping scheme, and equation set. To avoid the accumulation of energy at the smallest scales, dynamical cores need some form of artificial dissipation, which is either explicitly added or implicitly included as a consequence of the choice of numerical scheme. Ultimately, we only want this dissipation to target energy that is aliased because of the truncation scale, although that is easier said than done. This artificial dissipation will often mimic the real atmosphere, converting kinetic energy at scales below the truncation scale to thermal energy. But there is no one solution to apply targeted dissipation, and because the methods adopted are often ad hoc and without strong theoretical grounding, it is often glossed over in documenting individual dynamical cores. The implementation employed in each dynamical core is further rarely fully documented in publications, although it sometimes appears in technical reports. Finally, the coefficients employed in numerical dissipation schemes are often empirically determined, as there exists very little theory on how to properly choose these coefficients as needed to minimize the manifestation of unphysical features in the simulation. When reading over technical papers or documentation describing the implementation of these schemes, you may come across some of these terms that refer to artificial diffusion in the model. When it comes to explicit diffusion or dissipation, you might see reference to these terms: horizontal diffusion or hyperdiffusion, divergence damping, vorticity damping, external mode damping, Rayleigh friction or model top sponge layers, spectral backscatter schemes, or SGS dissipation. When it comes to implicit diffusion or dissipation, the amount of diffusion added could be implicit in the use of terms like order of accuracy, off-centering, or monotonicity constraints and flux limiters. When it comes to filters, which are designed to directly remove aliased effects, you may see mention of spectral Fourier transform filters, digital filters such as the Shapiro filter, and time filters such as the Aslin filter. When it comes to fixers, which are designed to restore global conservation properties that might have been violated by some other techniques discussed here, you might hear mass fixer, tracer mass fixer, momentum fixer, or energy fixer. In this lecture, we'll only be touching on the terms highlighted in red on this slide. We'll touch on horizontal diffusion, divergence damping, Rayleigh friction, order of accuracy, off-centering, spectral Fourier transform filters, time filters, and total energy fixers. These schemes are fairly common in the world of dynamical cores. The dissipation terms can be thought of, in some sense, as an additional term on the right-hand side of the evolution equation, in addition to terms for the dynamical evolution of each variable and the time tendency from the physical parameterizations. Because diffusion, filters, and fixers are primarily designed to correct issues that relate to the artificial truncation that occurs in the dynamical core, they are usually considered as part of the dynamical core. With that said, certain physical parameterizations, such as turbulence or convection, can also have a dissipative effect on the solution. So, what does dissipation look like in real simulated fields? Well, there are a breadth of methods available for advection, and different choices in the numerical method and corresponding dissipation terms can produce very different signatures in the resulting solution. Here we see solutions from 8 dynamical cores running a pure advection test case as part of the 2008 Dynamical Core Model Intercomparison Project workshop. The more diffusive dynamical cores are associated with a broader, blurred-out signature in the tracer field and lower overall tracer densities. In this particular simulation, Ohm's slope limiter was disabled, leading to oscillations because of the tracer transport calculation. The choice of dissipation can have a pronounced effect on the solution. Here we're looking at 2 runs, each performed at approximately 1 degree global grid spacing. On the left is the CAM finite volume dynamical core with monotonicity constraint applied and divergence damping. On the right is the CAM Eulerian dynamical core with horizontal 4th order hyperdiffusion with its default coefficient. Both simulations are conducted with the 3D mountain wave test case, which features zero topography except for a conical mountain at 90 east and 45 north. Both solutions are stable for long runs. But which do you think is the correct solution? Certainly, I think it would be hard to argue that the CAM FV run wasn't more aesthetically pleasing. But the Eulerian solution does pick up on more fine-scale behavior, even if it does appear like spectral ringing. But that doesn't necessarily mean it's the more correct solution. So while we cannot say that either of these is necessarily the correct solution, as notably this test case has no analytical solution, we can see a clear signature of dissipation on the left and a smoother solution overall. So how does dissipation work mathematically? Well, there are many forms of dissipation. One of the most common is constant coefficient numerical viscosity. Numerical viscosity mimics physical viscosity except with an operational coefficient many times larger than the physical coefficient. This large value means that viscosity starts to act on wave modes that are above the truncation scale. As an aside, physical viscosity only works on waves that are of the scale of meters or less, and so this is far below the scale of any sort of resolved motion in an atmospheric model. Models that explicitly resolve the dynamical viscosity are known as direct numerical simulation, or DNS models, but such models rarely represent domains of more than a few hundred meters to a side. Particularly for high-order methods like spectral transform and spectral element methods, second-order viscosity tends not to be sufficiently scale-selective. That is, it has too much impact on longer waves and not enough near the truncation scale. As a consequence, it's common in these models to use hyperdiffusion or hyperviscosity, which uses powers of the Laplacian operator. that is, fourth derivatives and sixth derivatives, or even eighth derivatives. A tuned diffusion coefficient is employed in each case that depends on the horizontal grid spacing. As mentioned earlier, hyperdiffusion or hyperviscosity are employed because they are more scale selective. That is, it has less effect on longer waves and more effect on shorter waves. The effect of the diffusion operator can be quantified with a response function, such as the one shown here. Where the curve drops below 1.0 is where the diffusion operator has the most effect. This response can be thought of as how much energy is removed at the corresponding wavelength or wave number of the diffusion operator. The black curve shows the second-order diffusion operator, which has an influence across the whole wave spectrum. The red curve shows the fourth-order operator, which is more scale-selective and affects the higher wave numbers more strongly. Subsequent higher powers of the diffusion affect higher and higher wave numbers more selectively. When diffusion is present, a clear signal in the energy spectrum emerges. We see a clear drop-off at the highest wave numbers, which is associated with that loss of energy from the kinetic energy. At these scales, diffusion is responsible for removing energy so as to prevent accumulation at scales near the truncation limit. In these two plots, we can see the effect of the coefficient of diffusion on the amount of diffusivity experienced in a baroclinic wave simulation. The plot on the left uses the default fourth-order hyperviscosity coefficient in the Eulerian dynamical core, while the plot on the right uses a coefficient 10 times larger. The resulting solution on the right has far less spectral ringing and produces a smoother solution overall. However, it also produces a weaker extratropical cyclone, weaker vertical velocity, and less temperature mixing. When applied to the velocity field, the Laplacian operator can be decomposed into two components, an operator that only affects the divergence of the field and an operator that only affects the vorticity of the field. Since vorticity is associated with geostrophic wind, it usually exhibits fewer errors and so is more weakly damped than the divergence. As a consequence, it's common for models to damp the divergence more strongly than the vorticity, leading to a targeted operator known as a divergence damping operator. The form of these operators for both normal divergence damping, that is Q equals 1, and higher order divergence damping, Q greater than 1, are shown here at the top. The bottom of this slide shows how the divergence damping operator targets the divergence. Consider the horizontal velocity update equation as shown here in the first line, with an added second-order divergence damping term. Note that in this case, the operator is written as the gradient of the divergence, as opposed to the divergence of the gradient, as one would expect with a standard diffusion operator. If we then take the divergence of both sides of this expression, we obtain an update equation for the divergence. This hits on the gradient operator in the divergence damping to produce a Laplacian of the divergence. Thus, we see that this term has an effect on the divergence analogous to a second-order standard diffusion operator. Without divergence damping, the CAM finite volume dynamical core is actually numerically unstable for this test case. That is, it produces spurious noise that it eventually triggers negative temperatures. The top plot shows the smooth solution produced with standard second-order 2D divergence damping enabled, while the bottom plot shows the noisy solution produced with no divergence damping enabled. The bottom solution exhibits clear artifacts of an insufficiently diffused numerical solution, with energy accumulation occurring at the finest scales. The effect of insufficient diffusion can be seen clearly in the 700 hectopascal energy spectrum, as energy accumulates at the finest scales. With a well-behaved model with sufficient diffusion, we expect to see a decay of energy as one approaches the truncation scale. However, in the case of an insufficiently diffused solution, we see accumulation of energy at this finest scale, effectively a completely flat energy spectrum beyond wave number 50. Comparable solutions with second-order divergence damping and fourth-order divergence damping all show a reasonable decay of energy towards the truncation scale. The fall-off of this decay at the shortest scales, that is, deviation from the power law, is a consequence of viscosity acting on the flow. Viscosity essentially acts like friction, transforming directed motion into random motions, and thus changing the energy from kinetic to thermal. Notably, as horizontal divergence is closely associated with vertical motion, we anticipate that vertical motion will be suppressed when divergence damping is increased. In this plot, we see a histogram of precipitation intensity from the tropics. The yellow curve comes from a coarse resolution simulation with the CAM finite volume dynamical core, and shows appreciable occurrence of high-intensity precipitation events. However, when divergence damping is doubled from its default value, we get the blue curve, which shows effectively 0 precipitation events over 60 millimeters per day. Notably, less intense precipitation events are essentially unaffected in frequency. CAM finite volume shows much stronger vertical motion than the CAM Eulerian dynamical core, which follows the red curve in this plot. Because the model top has fixed altitude or pressure, there are consequences for wave propagation in the atmosphere. Vertically propagating waves can be reflected by the rigid upper boundary condition at the model top and propagate back to the surface. This animation shows vertically propagating waves generated by a small bump along the surface. Although completely unphysical, reflected waves can have an influence on meteorological patterns in the troposphere. As a result, additional diffusion is added to the model top to prevent waves from propagating out of the domain. These model top diffusive layers may be referred to as a model top sponge layer, Rayleigh friction, or radiative boundary condition. In essence, wave reflection arises from an upper boundary condition that is designed to prevent loss of mass to space, but as a result allows for the spurious reflection of waves. Rayleigh damping or friction is implemented to allow dynamic variables to relax to some fixed background value, with a prescribed timescale tau. Other forms of diffusion are also common, including a height-dependent diffusion coefficient that increases in strength as we approach the model top. Notably, there is no physical justification to either of these choices, except to prevent bigger unphysical consequences. Sponge layers and Rayleigh friction can have substantial impact on the characteristics of the simulation, particularly in the upper atmosphere near the model top. These four plots show zonal mean zonal wind from a Held-Suarez experiment, that is, a climate simulation with only idealized temperature forcing conducted over a sufficiently long period to obtain climatological statistics. In general, the stronger the diffusion applied, the lower the upper level winds. Fortunately, as long as these sponge layers are present far above the troposphere, the effect on lower level flow is minimal. Not all forms of diffusion need to be explicitly added, although explicit diffusion does give the model developer control over exactly how much diffusion is added to the simulation. Many numerical methods feature implicit diffusion, that is, diffusion simply that comes along with the discretization. One advantage of implicit diffusion is that it's strongly tied to the numerical method, so it can be designed to introduce the minimum amount of diffusion necessary for maintaining numerical stability. Notably, higher order methods are associated with implicit diffusion that is more targeted to higher wave numbers, or shorter wavelengths. This is because these methods tend to be more accurate for longer wavelengths, and so do not need diffusion to counter unphysical effects in this part of the energy spectrum. Implicit diffusion arises from a number of sources. Upwind methods and semi-Lagrangian methods almost always feature implicit diffusion. Monotonicity constraints and advection, which are imposed to avoid unphysical overshoots or undershoots of quantities like tracer mixing ratio, tend to crop extrema and so introduce implicit diffusion. Finally, time-stepping schemes, including most commonly employed Runge-Kutta methods, generally introduce a small amount of implicit diffusion by construction. Let's discuss a brief example of how upwind discretizations can result in implicit diffusion for the 1D advection equation. For simplicity, let's focus on the case where the wind is blowing from left to right and use a forward Euler discretization in time in conjunction with an upwind derivative in space. If we solve for the update at time qjn plus 1, we obtain the equation shown at the bottom of this slide. Note that this discretization is actually a simple interpolation equation with a single coefficient given by the Courant number u delta t over delta x. Observe that depending on the value of the Courant number, we simply sample some linear combination of qjn and qj-1n with coefficients whose value adds up to 1. If the Courant number is 0, then we are left with effectively no update. If the Courant number is 1, then we take the value at the previous spatial grid point. If the Courant number is 0.5, then we take half of one and half of the other. You can actually verify that if you were to use a semi-Lagrangian scheme with a linear interpolant, you would actually get exactly the same update equation. Observe, however, that unless the Courant number is equal to 0 or 1, the global maximum of our updated solution will never be as large as the global maximum of the initial solution. The linear interpolant will always lay between the values of adjacent points, so these sampled solutions at the next time step must also be less extreme than either of these points. As a result, our updated solution is always smoother than the initial solution, effectively the action of numerical diffusion. Here we see that updated solution. Observe how it is tending towards a constant state because of the action of the implicit diffusion. In fact, we can see how the implicit diffusion arises by simply rewriting this first expression in another form. The second form is identical to the first form mathematically, but now features a discrete central differences representation of the first derivative and an explicit second derivative operator. The first derivative operator uses central difference, which is known to be non-diffusive. The second derivative operator, on the other hand, is a diffusive operator that has the effect of smoothing out the solution. The results from swapping out the advection scheme in the dynamical core with schemes of various orders of accuracy, as applied to the baroclinic instability test case at day 9, are shown on this slide. Both the second-order scheme here and the third-order scheme feature monotonic limiters that introduce targeted nonlinear dissipation into the flow. At the top, we see the first-order upwind method just discussed. This scheme's dissipative character shines through here. The baroclinic wave is barely able to form because the solution is smoothed out with each time step. On the second line, we see the second-order Van Leer scheme, which already improves dramatically on the first-order upwind scheme. Indeed, it is only slightly smoother than the third-order piecewise parabolic method, shown here on the third line. This plot shows the 700 hectopascal kinetic energy spectrum from each of these simulations, taken out to 30 days. The first-order scheme shows a loss of energy at effectively every scale because of the over-smoothing from the scheme's implicit diffusion. The remaining methods are largely indistinguishable under wave numbers of 60 or so, which reflects how higher-order methods primarily target the energy in wavelengths close to the truncation scale. The result is perhaps as expected. The lower-order method exhibits greater energy dissipation than the higher-order method. Two flavors of the piecewise parabolic method are shown here, one with relaxation and one with only a positive definite filter. The simulation with only the positive definite filter is likely under-diffused, as there is a slight uptick in the energy at the shortest wave modes. Filtering can also be used to remove unphysical behavior from a simulation. We've already discussed the latitude-longitude grid and contrasted it against the more homogeneous cubed sphere and icosahedral grids. Notably, the latitude-longitude grid exhibits convergence of grid lines towards the poles, resulting in anomalously small cells. Recalling that with any explicit method, the maximum time step size is constrained by that grid spacing. This means that the time step size in these regions must be dramatically constrained. However, if we were to use that constrained time step globally, the computational cost would be greatly enhanced of the whole simulation. A smart solution was devised to deal with this problem. Since we know that the instability will manifest at the shortest wave modes, after each update we instead use a polar filter to simply remove those problematic wave modes. This approach is known as polar filtering, and is an effective strategy for solving the regular latitude-longitude grid's pole problem. However, this method is in effect removing energy from the system in the process. The polar filter is a form of spectral filter, meaning that it works in spectral space. Because of the orthogonality of the regular latitude-longitude grid, and the fact that the compression of the grid size only occurs in the longitudinal direction, this filter only needs to be applied in 1D along lines of constant latitude. The basic idea of this filter is as follows. First, we transform the grid point data along each longitude into spectral space via Fourier transform. Second, we set all spectral coefficients beyond a certain truncation wave number to 0, or multiply them by a damping coefficient. Third, we transform the field back into grid point space to produce the filtered grid point data. The strength of this filter is determined by the damping coefficient chosen, and can be a function of the wave number and latitude. Because the instability in the numerical method only appears at polar latitudes, this filter is often only applied poleward of 45 degrees north latitude. One drawback of spatial filtering is the need for all grid point data along the latitude ring. This means that the system will generally have poor scaling on parallel computer systems, because a large number of messages need to be exchanged in every filtering operation. Filtering can also be applied in time rather than space. Temporal filters are employed when the temporal discretization produces unphysical behavior, such as the checkerboarding effect from the leapfrog scheme. The basic leapfrog scheme is shown here on the right for an arbitrary nonlinear time tendency term. With the Robert-Aslin filter, the previous state of the system is pre-processed before being used in the leapfrog scheme through second-order diffusion in time, yielding the overbar phi term shown here. This counters the checkerboarding effect through temporal averaging. As discussed in the context of finite difference methods, not all dynamical cores inherently conserve mass. Over long integrations, this can lead to a substantial loss of atmospheric mass, transforming the planet into something more akin to Mars than Earth. As a consequence, these models sometimes employ a posteriori mass fixers to compensate for the loss of mass. Essentially, at the end of every time step, the global mass is computed and any deviations from the reference mass recorded. This difference in mass is then distributed evenly among grid cells to ensure the global total mass remains constant. However, in doing so, one needs to take care in the process to not disturb geostrophic or hydrostatic balance. This is an easy process in pressure-based hydrostatic models, where surface pressure can be adjusted after every time step. These mass fixers are not benign and can have pronounced effects on the final solution. Here we see how the employ of a mass fixer can affect the temperature field in the integrated forecast system over a long-term held Suarez-style simulation. In general, the model shows widespread cooling when the mass fixer is employed. This is largely because an increase in density must be compensated for with a decrease in temperature in order to hold pressure constant in the model. Because total energy conservation is important on climatic timescales, climate models also employ energy fixers to deal with energy loss in the model. Energy loss is far more common in climate models because energy is usually not a predicted variable, and because any of the forms of dissipation discussed in this lecture can lead to energy loss. Violations of energy conservation can lead to artificial drifts in the climate system, such as changes in ocean heat fluxes. In nature, total energy is conserved and consists of three components: potential energy, kinetic energy, and internal energy. At the spatial scale of turbulence, where dissipation is active in the real world, energy is transformed from kinetic energy to internal energy. In atmospheric models, diffusion can cause a loss of kinetic energy, but there is not necessarily a way to replace it with other forms of energy. Thus, whenever diffusion is present in the model, either implicit or explicit diffusion, an additional mechanism is needed to replace the energy lost through diffusion. This can either be through frictional warming, in which case internal energy replaces the kinetic energy lost to diffusion, or through modifying the dynamic fields through spectral backscatter type schemes. In summary, diffusion and filters can be employed to help maintain numerical stability, removing unphysical effects such as numerical instability and replacing them with unphysical diffusion. Some diffusion, whether it be explicit or implicit, is always needed to prevent accumulation of energy near the truncation scale. The accumulation of energy occurs because of the energy cascade in the atmosphere from large scales to small scales. But these techniques must be used selectively, and the consequences known prior to their employ. One word of caution: it is easy to compute nice-looking, smooth, highly diffusive, and generally inaccurate solutions. But it is difficult to produce accurate, physically consistent solutions. Okay, that's all for today's lecture on diffusion, filters, and fixers. That also wraps up our discussion on the atmospheric dynamical core. In the next lecture, we'll be discussing supercomputers, the history of supercomputing, and how they're employed for climate modeling.